How many of you are planning to take 3550 modern physics? So the instructor we had scheduled for that was Dr. Heath, but because he passed, no, I've been scheduled to teach that. I'm sorry, spring. So in fact, I'm going to, we're going to go, there's several parts to that course, but some of it will be to do more of the quantum mechanics. So we're going to be doing, using this textbook at the beginning of the course. And then we have some more other things we're going to be looking at, particle physics and some other things that aren't covered specifically in this textbook, special relativity as well. So we'll begin with quantum.
30, 50?
35, 50.
35.
Yeah, it's called modern physics. Kind of an odd course, and the department had not been teaching it, but for several years, but it was still on the books, and they decided for various reasons to put it back into the requirement for undergraduate majors. So I guess, in fact, those of you who are majors are required to take the course. As of your class this year, will be the first year, I think, where they're required to take it. And it normally is kind of a hodgepodge of stuff, not very deep. Kind of more discussion about than really learning the material. And I don't like doing that. I'm going to give you some stuff. It's going to be at the appropriate level. But it's, you know, like this textbook is, you're really learning quantum mechanics. You're not just learning about quantum mechanics. You're actually learning mathematical formalism, because in modern physics, the mathematical formalism is the core. So really, we'll be doing that. So we'll be continuing the study of quantum mechanics in that course, and also, as I said, doing some special relativity part. Okay, so let's see. We're doing some brief introduction to operator algebra in quantum mechanics, which is central to the study of the quantum mechanics, because we have the wave functions and we have operators. The operators extract information contained in the wave functions about ensemble atoms. So whenever we want to compare to some experiment, there will be an operator associated with that, which is used to extract the ensemble averages, measurements, those things. So for example, we've had a couple of operators. This operator, which is associated with the momentum. There is a sign error in text. There should be a negative sign. And then a positive sign, there's a positive sign in the text. Equation 336. 366. Not many errors in the textbook for first edition. Three of those sorts of things, but there's one. We have another one which was called the Hamiltonian. And so those are two examples. We'll keep encountering more of these. Yes.
In the textbook, it had E it had the potential energy as a function of x hat.
Yeah. So when we're dealing with functions of x, these operators are acting on x. Then x is a number. It doesn't need to be an operator, but so you'll sometimes see it as written as x hat or just x. So x hat operating on a function of x. And same thing, b of x hat. The reason for that is because when we were also working with the Fourier transform of this, a function of k. And so in that case, when you're wanting to have an x acting on this, there's a relationship. I'm not sure of the sign here. We're dealing with functions of k. then the operator is the derivative with respect to k. The x operator is the derivative with respect to k. It's kind of a funny thing. So that's the reason for this. I don't expect you to remember it. Sometimes you'll see x hat over here, and if you're dealing with functions of x, then x hat is just a number. Okay. So that's the reason for this funny notation. Here's kind of funny. What's the x hat? The x hat is just x. When you're dealing with functions of x, it's just x. X that occurs in the function. Okay. And we had, for example, a free particle. In which case the potential energy is 0. And the Hamiltonian for a free particle is the kinetic energy. Okay. All right, so let's suppose we have a plane wave. For example. A plane wave. Where do we encounter the plane wave as a solution to the time-dependent Schrodinger? What physical system is the plane wave the pure mode?
Particle in the box.
No. Remember, the particle in the box pure modes were the signs that vanished outside.
Free particle.
Free particle. Plane wave is a pure mode for the free particle. Hamiltonian was this, and this is a pure mode for that problem. Yes, ma'am.
Okay, so if the Hamiltonian for the free particle is that, that's the Hamiltonian for what? General?
This is a more general case where there's some potential.
Okay, so there's not like a specific name, it's just general.
Yeah, that's right.
Okay.
Yeah, and we've done some specific cases here. The potential is not 0. Those were the step potentials, delta barrier, delta well, particle in a box, oscillator.
So you kind of sub it out as needed.
Yeah.
Thank you.
So this is the general expression that has these specific cases that we've considered. And the free particle is the case where the potential is 0. Particles sliding along. Okay. All right, then for the free particle, we notice that when I apply the free particle Hamiltonian to the plane, I'm going to write this out specifically like this. Okay, and for the plane wave, remember we have this relationship dispersion relation for a free particle. Okay, so we apply this to here. Okay, what does that give? Second derivative. Yeah. I'm specifically asking what does the second derivative give acting on the exponential?
I apologize. Negative h squared.
That's right. Okay, which is then just h bar squared k squared over 2m. And remembering that the momentum is h bar k. This is just p squared over 2m. This is just the energy. Which is also h bar omega. Okay. So we have this interesting relationship. Hamiltonian for a free particle acting on the plane gives a number, specifically the energy times the plane. Interesting equation. The operator acting on this special function gives the energy times that function. See, most times an operator, when it operates on something, it alters the function. Like if it's a derivative acting on ordinarily on a function, gives you a different function that writes the derivative. So this is a special case. In fact, this is an example of a pure mode. Another way of saying pure mode in general is that. So in this case, this is a special function. It's also true for just the time independent part. We had was little x, little psi. So another way of writing a condition of pure mode, remember what we did originally with a pure mode. Originally, I introduced it this way. All the parts have the same frequency, there's just one frequency. But what we found is this is also a different way of writing the pure mode, which is the spatial part satisfies an equation like this. Hamiltonian acting on the spatial part of the pure mode gives back just an energy times the pure mode. Yeah.
But it's not true for like the full like psi of entity.
Well, it is. I mean, but H doesn't act ordinarily on T, right? H just there's no time dependence here. Right. So it's true for both. But this is what I'm specifically interested in. This is the time independent Schrodinger equation. Okay, remember we made this assumption for the pure mode and substituted this into the time dependent Schrodinger equation. And that gave us the time independent Schrodinger equation, which is written like this. Lots of examples of this. In fact, all the ones that I wrote down here, not the scattering, but the bound state problems. All the bound state problems are like this. Did the particle in the box, did the delta well, briefly went by quick, simple harmonic oscillator most recently. These were all bound state problems, and they all were differential equations of this form, for different potential energy in each of these cases. Yes.
Forgive me if this is kind of trivial, but like, is it more of a notation point?
No, it's not. It's much more. And that's what you're about to see. All right. Yeah, this is much more than just notation. Equations of this form are have a special significance in quantum mechanics. They're called eigenfunction equations. Or eigenequations. Eigen comes from German meaning same. So an example of an eigenequation is some operator acting on some function gives back a number times that function. That's an example of an eigenequation. This is called the eigenvalue, the number. And the function has lots of different names, sometimes called an eigenfunction. You'll also see it called an eigen vector or an eigenstate. See those, all those terms mean the same thing. So eigenfunctions, I think what he mostly refers to it in books. It's a function, it's a special function for this particular operator. This special function, when acted upon by the operator, just returns a number times that same function.
Yes, sir. Because in the book, he says something along the eigenstate for particular purposes, and somehow when we say eigenstate, we're referencing something along the ensemble somehow even here. And the reading of pages, I think it's like 146. Like when we say eigenstate, we refer to this.
I don't understand the question.
I was just saying, like in physics, do we say eigenstate in particular?
All of these are the same. These all mean the same thing. Eigenfunction, eigenvector, eigenstate. It's a reference. It all means the same thing. These special functions are called sometimes eigenfunctions, sometimes eigenvectors, sometimes eigenstates. And they're all eigenfunction of that operator. So this depends on the operator. Different operators will have different eigenfunctions. This is an example. The pure mode is an eigenstate of the Hamiltonian. Originally, we started off this way. But now we see that the energy is the eigenvalue associated with the Hamiltonian operator. The eigenvalue of H. So the energies that we found in these bound state problems are the eigenvalues of the Hamiltonian for each of these problems. I think it's going to be helpful if I spell that out. And the eigenfunctions are the ones that we found before. So let's go back to the particle in a box as an example. Remember, the potential energy looks like this. It's infinite outside of a region of length L. And so we found the solutions to the Schrodinger equation for this. So the Hamiltonian is equal to inside, it looks like a free particle, but it's zero inside, but infinite outside of blocks. Okay, remember we then found we solved the time independent Schrodinger equation. We found an infinite number of such functions, infinite number of solutions that were indexed by the quantum number n. Wave function outside vanishes and with the simple form inside. And the energy associated with each of these is this, and these were indexed by an integer, positive integer. Infinite number of these with an associated energy spectrum like this. These are the eigenfunctions of the Hamiltonian for the particle and the eigenvalues. That's an example of an eigen equation for the Hamiltonian. Let's look at the simple harmonic oscillator. Okay. So the wave functions are these, there was some constant times Fermi polynomial. I think this is right. I think these are correct. If I remember correctly. A couple of homeworks ago, 1 or 2 homeworks back. That's the Fermi polynomial, so it's just a polynomial of order n. In this case, we, for no good reason, we index. The index begins with 0 by historical convention. And the energy associated with this frequency which is the classical frequency. Simple harmonic oscillator is a classical example of a particle of mass m on a spring constant k. So here are the eigenfunctions and eigenvalues associated with this operator. And x here, this is true for all values of x. X goes for minus infinity to plus infinity. Okay, so these are examples of this. And notice that in most of these cases, we have some kind of index associated with this to separate these different solutions. Use the index n. So these are referred to as the quantum numbers. Just some way of indexing the different solutions, keeping them separate. And the energy spectrum here is different than this spectrum. These are evenly spaced all the way up. These, the spacing keeps increasing the higher. So those are examples. Another example was a free particle, which we just did. Just like that. Okay, so what are the pure modes? Just wrote them down. Plane modes. Omega has a special relationship. Actually, we should just start. Let's put it this way: just e to the IKX. We're just writing on the spatial part. Okay. The those are the eigenfunctions. The eigenvalues. That. And notice the index here now is k. K is a convenient index, but k is not an integer anymore. K is any real value. Well, we can index the solutions by k. We could put a subscript here on this just to indicate that it's the plane wave with wave number k. And then E has that index as well. So we could write it. We can write all of those in the same way. Okay, but so far it looks kind of like notation, just noticing a kind of general aspect of all of these, but we're about to make it something more here than just kind of notation. Okay, so far, so this is just kind of looking backwards, looking back at what we've done. Just noticing that that was what we did. And so we had the time-independent Schrodinger equation. This is back an example of an eigen problem. Okay. All right, now here's an interesting thing. Let's go back to the free particle. The free particle, the plane wave, is in fact an eigenfunction of H. So a plane wave is an eigenfunction of H for the free particle. Okay. The plane wave is also an eigenfunction of P hat. Let's check that out. Let's apply P to the plane wave. Let's just leave G for our case. Or P, right, it's P. So in other words, the plane wave is also an eigenfunction of the P operator. Well, that's not too surprising because the Hamiltonian for the free particle is just P squared. And so if if P hat acting on the wave function gives back a number, then P squared acting on it will also get the same number. Let's try that. P squared acting on the UV activity hat. P hat times P hat. The one on the right side is going to act first. It gives just a number. Now the number just passes through, not X, it's just a number. So it passes through the operator P. And then the operator acting on the plane wave gives back another P, so it's just P squared. Okay, so P hat, the plane wave is an eigenstate of P hat, it's also an eigenstate of P squared. And also an eigenstate of K. Squared over 2n. Okay, so the plane wave is an eigenfunction of both of these. And here's where things start to get significant. Okay, so suppose we have two operators. Each one will have its associated eigen system. The eigensystem is a combination of the eigenvalues and eigenfunctions. Each eigenfunction has an eigenvalue. So let's look at the eigenfunctions of A. So the eigenvalues there's a bunch of possible values at A. And the eigenfunctions, each one is associated with the eigenvalues. We put a little A subscript on the function to identify that function is the one that has the eigenvalue. So this together, the eigenvalues and eigenfunctions are the eigensystem of well, B also has a set of eigenfunctions. I'm going to use a different symbol. Pi. These are also these are the eigensystems. So we have B and the function set of functions. This is the eigensystem. Okay. So we found here an example of two operators that have the same eigenfunctions. Here, plane waves or eigenfunctions of the Hamiltonian and also the momentum. In general, if these operators commute, then can form an eigensystem, compute, so then we can form a set of functions which are eigenstates, eigenfunctions of both operators. And that's what we found over here. So let's check the commutator of H with P. For the free part, this is the free part. I'm going to write this is free particle because it's not generally true that the Hamiltonian will commute to P. So let's take a look at this. The Hamiltonian, so remember this is H. Remember, this is supposed to be acting on something. always implicit in these operator equations. These operators are going to act on something. But I'm going to start writing the operators without the function that they're acting on. Just kind of drop those out. It's always implied that the operators are going to act on something. Okay, and the free particle is p squared over 2m p squared over 2m. Let's factor 1 over 2m. Here we have p cubed minus p cubed. And you get 0. So the momentum operator commutes with the free particle Hamiltonian. And by this theorem, then I should be able to find the set of functions which are eigenfunctions of both the Hamiltonian and the momentum operator. And that's what we found. Plane waves are simultaneously they're eigenfunctions of both operators. So that's an example of this larger theorem. So in fact, we would index the functions with both eigenvalues. So I'm going to have an eigenfunction which is labeled with 2 indices. 2 eigenvalues. If A acts on this, it gives little a. If B acts on this function, it gives little b. And that's an example of what we had here. H acting on the plane wave gives p squared over h bar squared k squared over 2m. P acts on this h bar k.
For the commutators, so is every eigenfunction of A an eigenfunction of B, and every eigenvalue of A an eigenvalue of B, or there's some that they share and some they don't?
You can form an eigensystem so that they're all both an eigenfunction of A and an eigenfunction of B. Yes.
For the A and B operators, do they have to give a number for this to be true?
Yes. This is going to be very handy when we go to 3 dimensions. Doesn't seem like it's really going to be a big help. This and this so far because we've got only a limited number of examples. But when we go to studying 3-dimensional systems, we're going to use this as a way of implementing an understanding about symmetry of the system. So the symmetry of the system will be expressed in terms of operators. And that is going to be really interesting. For example, let's take an example. Here's another one we haven't done yet. Let's go to the simple harmonic oscillator. Okay, I'm going to have an operator, let's call it script P. It's a parity operator. Script P takes a function of x and flips it to the negative, the function of the negative of x. Right. P commutes with h, this particular h, because everywhere if I flip x to negative x, 1/2 kx squared is the same. This is a way of saying that the potential energy is symmetrical in x. If I flip x to minus x, the problem looks the same. So the Hamiltonian isn't changed by operating with P. So I can operate with P and then H, or the other way around, it doesn't matter. Yes.
It's the P operator, what's it called?
Parity. Flip x to negative x. Okay, so the parity operator is an expression of the symmetry of this problem. This problem is symmetrical, left and right. Left and right are the same in this particular problem. So if I flip x to negative x, I shouldn't alter the Hamiltonian potential energy is the same. So this is an expression of symmetry. D of x is the same as negative d of x. So let's look at the eigenfunctions again. So the ground state was just a Gaussian. The first excited state was x times a Gaussian. Second excited state, oh, I can't remember, 3x squared minus 1, something like that. A polynomial that has only even powers of x. And the third state is something times x cubed plus something times x. These are, just to be clear, these are the ones that are on different page. Page 141, 140 and 141. These are the eigenfunctions of the Hamiltonian for the simple harmonic oscillator. All right, let's apply the parity operator to each of these. What happens to this function if I act with P on it? If I switch x to minus x, nothing happens. So P acting on ground state is +1 times the ground state. It has an eigenvalue of 1. What happens if I act on this function? Excited state. Yeah. So I can write that as -1. Remember looking at the pictures of these functions. This function is just a Gaussian, nice and symmetrical. This function goes like this, it's an odd function. Yes.
Where does the +1 and -1 come from? Like what is that?
Well, it just says if I hit the parity operator on this, this gives back the same function.
Oh,
But if I hit this one, it gives back the negative function. But I'm writing as a number like this because I want to write as an eigenfunction problem. So the eigenvalue of the parity operator is +1 here, -1 here. Okay, the next one was a function that looks like this. Around the origin. That's an even function. So what do I get here? Okay. This one has an odd polynomial. Polynomials involving only odd powers of x. So if I flip x to -x, the polynomial flips to negative. Now it looks, has something more like this. Go back to your drawings of those functions. So this is even, odd, odd. And the pattern continues. Every other one is even, every other one is odd. Okay, so what we have then is accomplished. We have these states are eigenfunctions of H. Here, and they're also eigenfunctions functions of the parity operator, see, I guess we go -1 to the nth. N is even, parity is plus, is even is odd, parity is negative. It's an odd function or an even function. We're going to find lots of this coming up. The study of symmetry in quantum mechanics first, it makes it a lot easier to understand what's going on, but it's actually got a lot about the nature of symmetry expressed by the physics that we've got. Symmetry is going to show up, for example, in the dynamics, in this case, in terms of the pure modes. The fact that the potential is symmetrical, it's an even function, shows up this way, that the eigenfunctions, that they can be made eigenfunctions of both operators, symmetry operator and the Hamiltonian.
This isn't like math hocus pocus, right? Like this is like tested and like.
Oh, yeah, correct. Sure. Yeah. It's an expression of the symmetry. And it's not, shouldn't be surprising to you to see that the dynamics of the system reflect the inherent symmetry present in the system. Right? Yeah, I guess. So let me expand on that just a little bit, and I'll get to your questions. So we have the free particle, right? And that commutes with the P for the free particle. Well, what is the P operator? Remember, the P operator does something. Right, yeah. Does something specific.
We used it to skip the Fourier transformation, right?
Yeah, that's true. But it does something. The derivative operator does something. Showed you in class. But why once? I mean, I didn't show it to you once, but why quick?
Well, P.
Yeah, it does pull out P, but it does something more. It translates the function. It's the generator of the translations. Okay, so if I translate the free particle, the energy doesn't change because there's no potential energy. It's flat. Okay. And so this is another symmetry. It just wasn't obvious. This says that the Hamiltonian is translation invariant. Translate the potential and it doesn't change. So in that case, for the free particle, the Hamiltonian is P. Another symmetry operation. Translation invariance. Remember, if you have a particle sliding on a constant potential surface, there's no force acting on it. The momentum is conserved. Okay. So this is going to start being really helpful to us. All this symmetry that's present will help us to catalog the states, but also to understand physically what's going on. Because the symmetry shows up in the solutions. Yes.
Just saying that the Hamiltonian, in this case, the free particle is translational invariant.
Yeah. He is the generator of translations. He translates. And so this expression says that the Hamiltonian is translation invariant. Another symmetry of this particular problem. Free particle problem. No, this is the momentum. That's what I was trying to. Yeah, my handwriting is not good enough. This, yeah. The fancy script P. This is lowercase, big uppercase things. The parity operator does this, flips. So it has left-right symmetry. So anytime you have a symmetry, the operator associated with that symmetry operator, will commute with a Hamiltonian. Then the eigenfunctions can be set up as simultaneously eigenfunctions of the Hamiltonian, that is pure modes, and eigenfunctions of the symmetry operator. Beautiful. This is where group theory comes in, by the way. I highly recommend a course in group theory, or if you don't get a course, you should study it. It's an extremely elegant subject. It has a lot of applications in physics. Symmetry built into the problem should show up in the solution some way. That's the study group theory.
For H and P, if they commute, shouldn't their eigenvalues be equal?
No. Not equal. So let's go back to this. The axon is going to get a different eigenvalue. So let's do this one and then do this one. Okay, so Bx first, we get a number B times the same function, and then Ax on that same function, we get a number A. This is A times B times the same function. And this does it in the reverse order, but still spits out the same function. B times A times I, if you use difference, is 0. They don't have to be the same. A and B don't have the same eigenvalues.
Thank you.
Parity operator is an example. You get even or odd functions, plus or minus 1. But the eigenvalues of H are the energy, not plus or minus 1, but the energy spectrum. Here, the eigenvalues of H are the kinetic energy. The eigenvalues of P are the momentum. They're related in this case, but they're not the same.
So psi is the same, but A and B are not.
Correct.
Thank you.
I write the two indices down here to note that it's simultaneously an eigenfunction of both operators, A and B. So I have two indices down. So I guess if I were doing that, I would put down here the parity 0 plus 1 minus 2 plus 3 minus. And that notation was kind of redundant because in this particular problem, the parities are so easy, plus minus plus minus plus minus. But to write it this way, I guess we could do it. It also implies, the theorem implies there's a second part. If the commutator is not 0, then there are no mutual eigenstates. And I'm out of time here. So let me give you, we did one just at the end of class. You had some homework on it. Example of a pair of operators that do not commute.
Excellent. Yeah.
Right. You cannot find eigenfunctions of both x and p. Here's some other examples. The simple harmonic oscillator with p does not commute. Cannot find eigenstates. They're both eigenstates of the Hamiltonian and the momentum operator. So the eigenfunctions that we were looking at cannot be made simultaneously eigenfunctions of both of these operators. Unfortunately, we're running out of time. But your last thing has to do with, well, I really don't have time to cover it, but we'll talk about it next time. Very last part of this. So as an immediate application, I could say this in 30 seconds. You have the electron, the next chapter is electrons moving around a proton, hydrogen atom. We're finally getting to the hydrogen atom after all this work, which is one of the things we wanted to understand. Okay, so the electron, so let's just take the electron away. And the potential energy of the electron moving around the proton is just dependent on the distance, 1 over r. Is there any symmetry in that? Spherical symmetry. I can take any axis and rotate. Close your eyes. I'm going to pick an axis and rotate. Open your eyes. You can't tell if I've done anything to the proton, right? It looks the same. So the spherical symmetry should show up in the wave functions and the spectrum of energies. And in fact, that's what we're going to see. But the symmetry of the hydrogen atom is very simple, spherical symmetry. So the eigenstates for the electron moving around should reflect that. And that's what we'll see in the next chapter. Yes.
Will that also show up, is there a symmetry involving the A field as well, or that's considered a potential?
Sure it is. But the A field, there's, the A field is not uniform. And what they do is changing from one place to the next. If you're not uniform, then the translation operator doesn't need to think retarded.
So that means the phi field is somehow.
No.
Sorry.
You're trying to make a generality that doesn't exist. The phi field only for the photon. The electron moving in the influence of the photon. Only in that case. Only in that case.
I was curious, is there anything in there, any symmetry with A field does too, or?
There's no A field for the electron moving around the photon. What generates an A field?
And just after they started by,
Right. The photon has no input.
wait, how can? If it's orbiting around, we're not looking at it moving. But we're acting as if it.
You're looking at the electron. The electron generates an A field, but not the photon.
Okay. Oh, so there's no way there's no symmetry, one's only doing, okay, I see.
The proton does not generate an A,